History of Mathematics, and Science and Civilization of India. And today I will devote this communication to the Sulbasutras, a topic appertaining to both subjects. We hope to send and bag the complete edition, translation and commentary of the four principal Sulbasutras, edited by the Indian National Science Academy in 1983. 1 century ahead, in 1875, as you see, the discovery of this kind of text was due to Georges Thibault with his arch article on the Shulva Sutra, and also with his edition with commentary of the Bodhayana Shulva Sutra and the commentary by Dvarkanatha in a periodical called The Pandit, edited in Banaras between 1875 and 1877. Actually, this followed other publications about Indian mathematical works in general. In 1817, Colebrook wrote his algebra with arithmetic and mensuration from the Sanskrit of Brahmagupta and Bhaskara in London. In 1834, Charles Wyche wrote a long article about different Indian mathematical works. And also in 1874, Kern edited the Aryabhatiya with the commentary Bhatta Deepika of Paramadishvara in London also. Already in the meeting of the Société Asiatique, in Paris on May 1878, Mr. Rodet gives some explanation about the mathematical measures used by the Brahmanists, as he called them, in the construction of their altars. The Sanskrit treatise, which deals with these interesting questions, has been recently published in India, they say, with commentary and English translation. Of course, this alludes to the edition by Thibault some years ago. Actually, Léon Rodet was the first French Sanskritist who interested himself in mathematical Indian works. He wrote 3 articles in the following years, in 78, 79, and 80, 3 long articles about mathematics and especially Indian mathematics. And some of his articles addressed to the content of the Shulba Sutra, as we will see a little bit more later. To this list, I must add the study by Vibhuti Bhushan Datta, The Science of the Shulba, edited in Calcutta in 1932. And if I may, also my own book, I published in Geneva in 2016. And happily, my book is in French, but I hope to translate it into English if I can find an editor. Now, about the Shulba Sutra, treatise of the court, there are practical manuals giving the measurements necessary for the construction of the numerous structures needed by the Vedic ritual. By instance, there is a Garapatya, which is a oath altar sphere, which is round and represents the earth. The square is represented by the Hahavaniya, which is an offering fire, which figures the sky, abode of the gods. And there are also some trapezoids called Vedi, offering table, whether with curved sides or with right sides like the Mahavedi above in the figure. This Mahavedi has 2 shronis, that means hips, which in fact are the corners, the western corners, and 2 amsa, that is shoulder, which are the eastern corners, as of an animal looking eastward. Of course, these structures were always disposed symmetrically to the west-east line called the Prachi line or the Prishtya line. And usually the Mahavedi also bears a large altar or Agni made of 1,000 bricks arranged in the shape of a bird of prey called Shenachit. Shenachit, like here. So you see there are 1,000 bricks arranged in 5 layers of 200 bricks. And you have the figure of one layer here. You can count, but you won't have the time that there are 200 bricks on that layer. No, this Agni must have an area of 7.5 square purusha when it is constructed for the first time. 8 purusha and a half in the second time, and 9 purusha and a half in the third time, as it is prescribed in the second chapter of the Bodhayana Sulbasutra. That means that the altar is firstly constructed as a squared bird of prey, where you have here the wings, and then you have also the tail and its extension of the tail and also of the wings in order to make 7.5 square purusha. Of course, every square has 1 purusha of side. And from this figure, very simple squared figure, you have to transform into a Shenachit with curved wings, as we have seen, or into other shapes like the Ratachakra-chit, or the Ubayata Progachit, which is a rhombus, or into a Kankachit, which is another bird with legs this time, or into a Kurmachit, which is, of course, a turtle, and many other forms whose areas must always be the same, that is 7.5 square purusha for the first construction. So this prescription that all these Agnis have to be of the same area means that the Sulbasutras must propose some area invariant transformations, like the quadrature of the circle. But since the square is the very basis of everything, let us first explain its construction. So this is the first construction of the square with only circles. So first you trace the east-west line, the Prachi, and then you put a peg here. A peg to which a cord ended by 2 loops can be attached. If you do that, if you attach it by 2 loops, you have this kind of circle. But it can also be attached by only 1 loop, which will give you this kind of circle, or this circle. No, you can draw a straight line through the intersections of these 2 circles in order to put 2 more pegs here and there. And with these 4 pegs as center, you can draw 4 little circles like this. And you will have very easily know the square. So this is the first construction of the square. But I will now show you another construction, which is also more interesting about the content of the Sulbasutra. And this is this one. Here, you have a first sutra saying Ataparam, means another what? Another construction, Karanam. This is the commentary, of course, which says that you have to add Karanam. So this other construction works this way. You put 2 pegs to begin with, and of course the distance between the 2 pegs is the side of the square. Now, you use a cord with 2 loops at its end, and this cord must be as long as twice the side of the square you want to construct. And in fact, you put a mark in the middle of the cord. So the cord will become like this. So this is a cord double of the side of the square, But of course, you have to think that this chord is only attached to the first peg, that means the left peg, not at the right peg. At the right peg, in a way, there is the mark. No, this is, as say the text, in order to draw the prachi. The prachi is, in fact, the side of the peg, the side of the square, sorry. Next sutra, you have to take the western part of the chord, and on that western part to put a mark here at 3/4 of the length of the side. This is called the nyanshana, tanyanshanam, which means that in fact the chord will have to be bent with the help of this mark. Then you have another mark which is made in order to have the shoulder, the amsa. You see, amsartam is written in the text. And you put that mark in the middle of the western part here, the green mark. And then you bend the chord this way. So you bend it by pulling it at the red mark, so that the two lengths you have now in the chord is 3/4 times L and 5/4 times L. When reversing the chord to the right, sorry, I forgot this. Of course, with this length, you will have a right angle in that triangle. Now, when reversing the chord, you can have another corner to the east, another to the northeast, and another to the southwest, so that you can now draw the square. Of course, this construction means that the Sulbasutra knew Pythagoras' theorem, or rather, it's reciprocal. That is, if three numbers a, b, c satisfy the so-called Pythagoras relations a to the square plus b to the square equals c to the square, then the triangle whose sides have length a, b, and c has a right angle opposed to the side of the length c, which is usually called hypotenuse. For instance, here we had these three lengths, and if you put L equal 4, you have these three numbers, 4, 3, and 5, which are, of course, number A, B, C satisfying the relation a to the square plus b to the square equals c to the square, because 4 to the square is 16, 9 to the square, 3 to the square, sorry, is 9, and 16 plus 9 is 25, which is 5 to the square. In the Sulbasutras, of course, this property is expressed. But I call it the property of the diagonal and not the Pythagoras theorem, because it's not explained in a triangle, but in a rectangle. So the first sutra, 45, is the chord stretched across a square produced an area of the double size. This is what we call the square case. And the second sutra, 48, the diagonal of an oblong, produced by itself both the areas which the two sides of the oblong produce separately. This is the oblong or rectangle case. So let's say the Pythagoras theorem is separated into two cases, the square and the oblong cases. And the Sutra 48 continues with this, which is a list of different numbers playing the role of A and B in the Pythagoras relation. So you have 4 and 3, 12 and 5, 15 and 8, 7 and 24, 12 and 35, and finally 15 and 36. If you calculate the third side, that's the diagonals, in fact, you find 5. And these three numbers are called Pythagorean triplets. So you have also 12, 5, and 13, 15, 8, and 17 that you can figure like this, so that you can see that the blue square is completed by a figure with a L shape in a way that this figure contains a square number of little square. In this figure, you have 64 little square that you can arrange in a little square of side 8, of course. That's why it works. Then you have 25, 37, and 39. Now you can see that the sutras separate the, let's say, Pythagoras theorem in two cases, the square case and the rectangle case. The square case can be understood very easily with this figure. And this figure is also found in some vases of the Indus civilization, which probably means that the Indus civilization already knew this square case, at least the first case of the theorem. But the second case, the rectangle case, is of course not understandable with a figure. It needs calculation, as we have seen. Now we can have a look also at the wording in Sanskrit. The first sutra, 45, says that bhumim karoti, produce an area. So in the verb karoti, you have implicitly the idea of a square. Same in the Sutra 48, where you have Yat Pratak Kurutas Tat Ubayam Karoti. Again, you have the verb karoti or kurutas, which is another form of the same verb. And implicitly in these words, you have the construction of a square, which is not the case in Greek, at least in Euclid's element. So I will pass this very shortly. That were they remarked that the tetragonon, you know, the last word of the first line, explicitly said that you have to build a square. It's not only a verb here, there is a substantive to say that it's a square. In other texts, like this one by Diogenes Laertius, or this one by Theon of Smyrna, there is only one verb which implicitly says that you have to build a square. So this looks a little bit like the Sanskrit formulation here, but instead of the verb karoti, you have dunatai, which means can. And from karoti, you find karani, producer in Sanskrit. From dunatai, you find dunamis, and they have the same meaning, which is finally the square root. So there are some parallel to be expressed between some Greek text and some Sanskrit text. About geometry and ritual, you have of course remarked that in the Sulbasutra, the ritual is always there. We are making geometry, but it's about the ritual. In the Greek text, it's quite different, but you find some traces of a relation between rituals and geometry. In this text, for example, Apollodorus, the calculator, says that Pythagoras sacrificed an hecatomb, of course, to celebrate his discovery of the theorems. That means that Pythagoras sacrificed, probably ritually, 100 oxes. And there are other texts saying that he sacrificed only one ox, but there is definitely a relation between the ritual and the geometry. Now we will see, of course, the very famous circulator of the square, which seems to be necessary in Indian texts because, as I told you, the aim of the ritual is to put in relation the sky, which is square, and the earth, which is a circle. So the first transformation given by the Sulbasutra is the circulator of the square. So you begin with a square, you take half of its diagonal, that you will turn to put it on the west-east direction, like this. And then with a third of what is outside the square, you will draw a circle. And this circle is supposed to have the same area as the initial square. That's the construction given by the Sulbasutra. Every Sulbasutra we know about the transformation of a square into a circle of the same area. But of course, the Sulbasutra, and this is a characteristic, always give the reverse transformation. That is the quadrature of the circle. And in fact, you find two quadratures in the Bodhayana Sulbasutra. And I will show you only the second one, which is very easy. You divide the diameter of the circle into 15 parts, and you remove 2. And that is what is called the gross side of the square. The gross side translates Esha Nitya. And Esha Nitya could be cut into Esha Nitya, which means the usual side, or Esha Anitya, which is supported by the commentary, which says Stula instead of Esha Nitya, which means gross, coarse. So that's why Thibaut probably translate this sutra as he did, using gross instead of usual. But as far as the Bodhayana Sulbasutra has also another quadrature, much accurate than this one, it's possible that the author of the Bodhayana Sulbasutra could have tried to say that it's the usual side, because this quadrature is the one which is found in every Sulbasutra. So it is usual. It is traditional in a way. Another transformation is very interesting. It's the square into a rectangle. Before that, in the Sulbasutra, you have the reverse. You have the transformation of a rectangle into a square. Now let's see this one. So you have to transform this square into a rectangle. And the sutra says you can cut it by the diagonal, then cut again 1/2 in 2 parts, and remove the 2 parts in order to build a rectangle, which is, of course, of the same area as the initial square. The problem is that this transformation is not general enough. Normally, you should be able to transform a square into a rectangle of any breadth you want, like this. For example, you cut it by the breadth of the rectangle, and you have a sutra in the Bodhayana Sulbasutra, it's the following, saying that you have to place, what is left, that means what is on the right here, elsewhere, but you don't know exactly where. So that Thibaut wrote in his edition that he doesn't venture on a translation of this sutra, as it doesn't clearly appear to what geometrical operation it refers. Happily, and then he also add, moreover, there seems to be a lacuna in the commentary. So that means that he couldn't translate this sutra with the help of the commentary, of course. But happily, I have found in 3 manuscripts from Pune, Tanjore, and Ujjain how to complete this commentary. And I will show you how it worked with the commentary. You have to extend this right side of the square, then through the point A to draw a diagonal that will cut the extended side on B. And from B, you draw a parallel to the top side of the square that will cut the extended left side of the square, so that this rectangle is the rectangle you wanted, because these 2 figures, the square and the rectangles, have the same area.